let's do some examples applying Stokes' theorem. Here we have the example that we started with in the first part of this lecture, where we directly calculated the circulation of the vector field F, whose coordinates are xy, 2xy, and xy, around the cylinder with radius 1, capped at z equals 0 and z equals 4. And what I mean by this is we have an open cylinder here, whose bottom part of the boundary is at z equals 0 and top part of the boundary is z equals 4. So we have an open cylinder cut off at z equals 0 and z equals 4. Well, previously we calculated the work done by this vector field on the boundary of this surface, and it required us to do two line integrals because there are two parts of the boundary of this surface. Well, if we think about Stokes' theorem, what Stokes' theorem says is that the surface integral of the curl of this vector field is the same thing as the work done by this vector field on the boundary, or the circulation of this vector field around the surface. So let's look at the ingredients requisite for applying Stokes' theorem. Well, to apply Stokes' theorem, what we would want to do here is take a surface integral over this surface. And in order to do that, we need to figure out what the normal vector is here. So let's start by parametrizing this surface. And since this is a cylinder with fixed radius, we're going to use cylindrical coordinates, and we're going to fix the radius equal to 1. So here we're parametrizing with theta and z, and our parametrization is the vector whose coordinates are cosine theta, sine theta, and z. So here, of course, we're suggesting that x should be set equal to cosine theta, y should be equal to sine theta, and z is just equal to z here. Well, if we look at the standard normal vector for this parameterization, that is, if we take the two tangent vectors by differentiating with respect to theta and then z, and then crossing those two tangent vectors, we end up with the normal vector given by cosine theta, sine theta, comma 0. And one thing to point out here is that even though this normal vector is valid, it's actually pointing in the direction opposite to the normal vector prescribed in the problem. In the problem, the normal vector points into the cylinder, but the normal vector we just calculated points away from the cylinder. How can we see that it points away from the cylinder? Well, we could plug in just one value of theta. For example, when theta equals 0, the normal vector is 1, 0, 0, which points away from the z-axis, not into the z-axis. So we have to keep this in mind as we do our calculation, that the formula we've derived for n is actually the negation of a correct formula. Well, what is the curl of our vector field? Well, if we apply the formula for curl, we end up with the vector negative x, negative y, and then negative x plus 2 times z. But since we have a parametrization of our surface, we plug in the value of x equals cosine theta, y equals sine theta, and z will be just equal to z in our expression for curl. So now we can look at the dot product of curl with the appropriate normal vector, because that's one of the ingredients in a vector surface integral. So when we take the curl of our vector field and dot it with the appropriate normal vector, here we have to remember to not use the normal vector that comes with our parametrization, but its negation, because its negation is the one that's compatible with the normal vector we're given in the problem. So here we're going to dot negative cosine theta, negative sine theta, 0, with the curl, which is negative cosine theta, negative sine theta, 2z minus cosine theta. And when we take that dot product, we get cosine squared plus sine squared, which is equal to 1. So now, according to Stokes' theorem, the circulation of this vector field around this surface is given by, well, that the notation for the circulation is the line integral of the vector field over the boundary of this surface. But Stokes' theorem says this quantity is the same thing as the surface integral of the curl of this vector field. And how do we take surface integrals? Well, we take the vector field and we dot with the appropriate normal vector, and then we integrate over the parametrization. Here we found that the dot product we're studying is equal to 1. So in the formula for surface integrals, we should just be integrating 1 over the domain of the parametrization. Here z ranges from 0 to 4, and theta ranges from 0 to 2 pi. Well, when we do the calculus here, we end up with 8 pi, and the units are Newton meters. This is exactly the answer we got when we did the calculation previously. However, here the calculation is dramatically simplified because we've applied Stokes' theorem and we didn't do the two individual line integrals. Let's look at another example. So here we have a curve depicted in the problem statement, and we are given a particular vector field. What is the curve we're given here? Well, this is a curve which is part of a surface defined over a domain. So the domain here is x squared plus y squared is less than or equal to 1. So this is the interior of the unit circle. And here what we're doing is we're looking at the plane given by z equals y plus 3, and we're only focusing on the portion of it that lives above this domain. So the idea here is that the curve we're interested in is the boundary of the surface obtained by only restricting the plane to the part that lives above this domain. So let's look at the data requisite to calculate the circulation of this vector field around this boundary. Well, we can parameterize this surface quite easily because we're given that z is y plus 3. So here we'll just use x equals x, y equals y, and z equals y plus 3. If we calculate the standard normal for this parameterization, again, we would do this by taking derivatives with respect to x and y and then taking the cross product of those derivatives. We end up with a normal vector given by 0, -1, 1. So we should pause to make sure that this normal vector is looking in the right direction. So here, the normal vector we've calculated has a positive z component, so it should be pointing upwards. And if we stare at this for a second, we realize that this is the correct normal vector, because if we move this normal vector to the outer edge and we look in the direction of the unit tangent vector, the surface is to our left, not to our right, which is compatible with positive orientation. Now we can look at the curl of our vector field, which happens to equal -2, 3, 5. Well, when we go to apply Stokes' theorem, we'll take the dot product of the curl of the vector field with the normal vector. And here everything is a constant, so we just end up with the number 2. So according to Stokes' theorem, the circulation of this vector field along the curve that we're given is the same thing as the circulation of the vector field on the boundary of our surface. And Stokes' theorem says that the circulation of a vector field along the boundary of a surface is the same thing as the vector surface integral of the curl of that vector field in the surface. And we just found that the curl dotted with our normal vector is 2. So really what we're doing is we're taking the double integral of the number 2 over the domain of our parameterization dA. And here the domain of our parameterization is the unit disk. So really what we're doing is we're taking 2 and multiplying by the area of our domain, which of course is equal to pi. So our circulation is equal to 2 pi Newton meters in this example. So we've managed to calculate a complicated vector line integral by using Stokes' theorem and calculating a significantly simpler vector surface integral. For our last example, let's look at an interesting example where we want to calculate the flux of a particular vector field. So here, in this example, we want to calculate the flux of this vector field, which is given by, in coordinates xy plus 1, -x times z, and -y times z. And here, the vector field has units meters per second. So this is a velocity field. So we want to calculate the flux of this vector field over a particular surface. And here the surface we're studying is the sphere of radius 8, centered at the point -374. Now at first glance, this looks like a very complicated flux problem because we have a somewhat complicated vector field, and we have a sphere that's not centered at the origin, and its radius is 8. Well, one thing I want to point out is that we could study this vector field by taking its divergence. Remember the power of the operator exact sequence. The operator exact sequence tells us that if we take the divergence of a vector field and we get the number 0, that means that our vector field is the curl of another vector field. So here, when we take the divergence, we're looking at the partial of the first coordinate with respect to x, plus the partial of the second coordinate with respect to y, plus the partial of the third coordinate with respect to z. And here, what are we looking at? Well, xy plus 1 with respect to x is equal to y. Negative x times z with respect to y is equal to 0. And xy plus 1 with respect to z is equal to, let's see here. This should be equal to 0. So have I made any error here? So the derivative of xy plus 1 with respect to x is y. Negative x times z with respect to y, this should be 0. And then negative yz with respect to z should be negative y. Okay, yeah. And so when we take the divergence here, we end up with the number 0. So this vector field is divergence-free, which means that f, this vector field, is actually equal to the curl of some other vector field. Now, back when we studied the operator exact sequence, I gave you a nice formula for figuring out a suitable choice for G, which is given by Poincaré's lemma. But the point for this example is that G doesn't matter at all. This is a particularly interesting surface because it is closed, meaning this surface has no boundary. So we're only looking at the outer shell of this sphere, and there is no boundary curve. So what does Stokes' theorem tell us? Well, Stokes' theorem says that the flux of this vector field F, well, that's the same thing as the flux of the curl of G, because F is equal to the curl of G. And Stokes' theorem says that the surface integral of the curl of any vector field is the same thing as the circulation of that vector field, in this case G, on the boundary of our surface. But since there is no boundary of our surface, this is forced to equal 0. And just as a reminder, the units here would be volume per second, or meters cubed per second. So since we know this vector field has divergence 0, we know that it is equal to the curl of another vector field. So the flux in this problem of F is the same thing as the surface integral of the curl of G, because F equals the curl of G. And then Stokes' theorem says that the surface integral of the curl of G is the same thing as the line integral over the boundary of S of G. And since there is no boundary here, that must equal to 0.